Solving linear systems in 3 variables is similar to solving linear systems in 2 variables. You use substitution and elimination, but you will need to use a little more strategy. Before we go into the algebra, I want to talk about the visual with the graph of what it looks like when you have the different cases of solutions. First of all, because we are dealing with 3 variables, all to the first power, so linear equations in the 3rd dimension, we are working with planes. The solution then is an ordered triple. Make sure to write ordered triples, ordered pairs, etc., always in alphabetical order. So if you're not given X, Y, Z, maybe A, B, C, it will always be written in alphabetical order. Now, a 3-dimensional system may have one solution, infinitely many, or no solution at all. One solution occurs when the planes intersect at one point, like down here. So that is the one point of intersection. You get one X, one Y, and one Z that make all 3 equations true at the same time. Infinitely many solutions can look like one of 2 things. They're either 3 stacks of paper on top of one another, so they are the same plane. All 3 equations are the same. And then the other case is when the 3 planes intersect in the same line, because remember, a line has an infinite number of points. Thirdly, no solution occurs when there is no common point among the 3 equations. So the planes don't intersect at the same place in time. So here, yes, these 2 equations intersect and form a line, so it looks like there might be infinitely many solutions, but when you check to make sure that beige or orange or whatever goes with like purple, okay, that forms a line, but then when you check when orange goes with green, it also forms a line, and then when you solve them together, you find that they don't all intersect at the same spot. Same here, there's no common point among all 3. So right now I'm about to go through the steps, which will be better understood through an example, but let me just cover these in general. You still start with 2 equations that contain the same 2 variables. The first step is very tricky with these because sometimes you don't have all 3 variables in all 3 equations. So you have to think ahead. So you have to make sure that when you pick your 2 pairs of equations that they are going to eliminate the same variable, or that, let me rephrase that, you have to make sure that you will end up with the same 2 variables after each pair of equations. So moving on to the second step, you select a different pair, eliminate the same variable, and then you get this new system. You've boiled it down from 3 variables to 2 variables, and then you solve that new system. And when it says solve the new system, that means find the value of both of the variables, and you do that before you substitute back into the original system to find the last unknown, writing your answer as an ordered triple. So jumping right in, we're starting off with a system of 3 variables in 3 equations. These are all linear. There are no variables multiplied together. All have powers of 1. This is the easiest type because we could do the same thing every time for this type of problem, but in general, we want to be strategic. So I'm looking, the y's would not be so bad to eliminate because these y's have an LCD of 6, these y's have an LCD of 2, pretty small numbers. Same story with the x's, 2 and then 3, or 2 and then the first and third would have an LCD of 6, as long as you choose 2 unique pairs. So there are many ways to the right answer here using the same general ideas. Now the z's have LCDs of 4 and 8. So I'm not going to eliminate the z's. I'm going to focus on either the x's or the y's. It's your choice. Because one of these y's already has a negative, that's going to make things a little easier, so I'm just going to eliminate the y's. So I like to start off by labeling my equations as 1, 2, and 3. That allows me to refer back to them very easily without having to rewrite the whole equation, and also as signposts for my work. So I'm going to take the first two equations and I'm going to eliminate the y variable. So I need to make a pair of additive inverses between these two. So then that means I need to multiply the first equation by 2, and then I'll need to multiply the second equation by 3. Make sure when you multiply that you distribute to every term on both sides of the equation. Zero times 2 is 0. Distribute the 3 to the second equation. And then add down. So the y subtract out to 0, leaving 3x plus 4x for 7x minus 14z is equal to 42. Now, that equation I will represent as a capital A. And I'm going to create an AB system which will then fuse together all three equations at the same time. But right now, I've only overlapped the first two. So that would be like looking at this here. But I need to figure out where all three planes overlap. So now I need to fuse two other planes together. And unfortunately, you can't do all three equations at the same time. So that's where all this strategy comes in. So now I'm going to look at equations 2 and 3 or 1 and 3. So because, again, in equation 2 I have a negative coefficient here, I'm going to use 2 and 3. So I wrote a couple things for convenience. Labeling step 1, I put together 1 and 2, and then for step 2, I am using a new pair. So 1 and 3 or 2 and 3 would work. And I wrote that pair down here again away from the original system. Now, if I was doing this without someone needing to follow my work, I would try to, every time I wrote an equation, to modify it as I need to for elimination. So, for example, when I rewrite the third equation, I could have doubled it already. But just to be clear, I wrote the new system, and now I'll go ahead and do that. So I will take this one, put a line through it. Because I'm modifying it, I'm going to double it. And then I'll add it together, this and this together, making sure that like terms line up. If they don't, then leave a space or just be extra careful. So these subtract out to 0. Now, that equation, big picture, is the B equation. And now for step 3, I need to solve this system that I just created. So I'm going to put into practice my recommendation that as I move A and B into the same system, I'm going to modify them based on how I see additive inverses between a pair of the variables. So I'm looking at the x's, and they seem really easy to eliminate. I just need to negate one of the equations. So when I rewrite A, I'm going to multiply by -1. and then I'll transfer b over unchanged. Now, the epic part of the next piece is when I add these two equations together, fusing them together, I'm representing that graphical overlap, that creation of this common ordered triple that's the same for all three equations. And I find that z is equal to -1. So finally we were able to squeeze out the value of one of the variables, and it's looking like all three planes or equations do overlap. So one thing that I would be remiss if I didn't say, right here in this system, notice I have the same two variables. At this point, if you don't, then that means when you created A or when you created B, you didn't strategize correctly. You always want to target the variables at the very beginning when you take two pairs, that you always get the same two variables in your A-B system. So now I'm not done with the A-B system. To solve it means that I know everything about it. So I have one of the two variables. So now I need to substitute back into one of these two equations. And let's see here. I'll just put it into the B one. So -20 times -1. Do the arithmetic in your head if you can. That would be +20 on the left, so that's a -20 on the right. And 7 goes into 28 4 times. Now, we have two of the three variables in our order triple. That's all the information that step 3 can give us. So now we need to go back to the original in any of the equations and that has a y in it. All three of them do. So I'll just substitute into the third one because that y is kind of all by itself. Or I like the first one better because it's like equal to 0 and the numbers are smaller. So now for step 4, sub into an original equation. So I'm going to pick equation 1, substitute in my x and my z. So notice this is a mix of substitution and elimination. The main strategy for this is elimination. I did it once here, I did it once here, and I did elimination a total of 3 times. And now I'm starting to do some substitution like I did here. You will always use elimination to solve these algebraically. So we have an 8 and a 1, which makes 9 on the left. So a -9 on the right for y value of -3. Now, if I thought at any time I made a mistake, you can substitute in these 3 values. So let me first write it as an ordered triple. Alphabetical order. Be careful with that because position provides information. That's the answer of where all 3 planes intersect in 3D space. Now, let's say I was given a multiple choice option and this was choice C. I could just go through, instead of all of this work, I could go through the multiple choice options and just substitute in one at a time to each of the equations. If it's true in all 3, then I know that's the solution. And then I get to save all this work and not make some arithmetic mistake along the way. Keep that in mind for multiple choice assessments. Let's look at one more example of a system where there's going to be one solution, but this time we don't have all 3 variables in all 3 equations, so the need for strategy has increased. So I need to think big picture here. If I eliminate these 2 variables, you only can eliminate what you have in common. What will I be left with? Well, this will be gone, and I'll be left with something y, something z. All right. Then, let's say I then take the second and third equations. If I eliminate the x's, I'll be left with just z. Oh, wait a second. That will give me the value of one of the variables. So what that means is this second and third equation is already our AB equation. So let me just go through. I like labeling my 1, 2, 3 equations. And then I realize that I already have A and B. Because we're working with a three-dimensional equation system, and this is already boiled down to two variables. So let's go ahead and solve them, and then we could substitute them back in here to find the third, and we'll be done, because we then would have effectively overlapped or combined all three of the equations. So I'm going to skip right to step 3. And these steps correspond to in the notes here. And you could also then see from here how we have an example of what each of the steps looks like. So now, because these problems don't always go the same way, I have to give you a variety. So let's take a look. I'm going to take 2 and 3, and as I move them, I want to strategize. If I take the z's, their LCM is -10, and for the x's, it's 13. So I'm going to go with the smaller numbers. And when I do that, I'm going to modify them as I go. So the second equation is going to come down here. I'm going to multiply that by 5. I'm going to eliminate the z's. So let's see here. Second equation will then modify to 65x plus 10z is equal to 10. Make sure to multiply that right-hand side of the equation. That's a common mistake, and then it throws off all your numbers. So now I'm going to modify the third one as I write it down. I'm going to multiply that one by 2. Very easy additive inverse pair here to create it. And I multiply that by 2. Don't drop your sign either. Don't make that positive by mistake. Now that I already have a pair of additive inverses, so that means their magnitude or distance from 0 is the same, and their direction is opposite. So one is on the left of 0, one is on the right of 0. So now I go ahead and add down like terms. Those subtracted out to 0. Oh, that's easy. Don't think at this time that, oh, there's no solution because 0 divided by a non-zero number is undefined. That's incorrect. I'm going to show this. When you see 0 over a non-zero number, that's just 0. So keep going. Don't stop. So that's step 3. Step 4. Whoop. That was almost a common mistake. I have not finished solving this system. So don't go to step 4 and work with the original system. I need to find the z now, substituting back in. This equation looks good. It's kind of smaller numbers. And I find that z is equal to +1. All right. Now I'm moving on to step 4. So I'm substituting back into the original. Let's see here. Which one has the y? Only the first one does. So I know x. I don't know y. I know z. So subtract one to the other side, and then write the answer as an ordered triple in alphabetical order. And again, if I was unsure, I could substitute back in, make sure it's true in all 3 equations at the same time. One more, because the strategy takes a little while to get used to. So if you want, pause the video and then see if you could come up with a path that will end up with an A-B system of the same 2 variables, but joins all of the equations together. So I'm going to talk out loud through this one. If I eliminate the x's in the first 2, I'll be left with something y, something z. Okay. And then if, let's say, I take 2 and 3 and eliminate what they have in common, I'll have something x, something y. That won't work. Those are not the 2 of the same variables. All right, so again, if I take 1 and 2 and eliminate the x's, and then if I take 2 and 3 and eliminate, they only have the z's in common. So that pairing won't work, or that selection of variables won't work. How about if I do 1 and 2 with the x's, and then 1 and, okay, interesting. If I do this here, and eliminate the x's with 1 and 2, and get something y, something z, notice y and z is already set up for me in the third equation, so I would be able to jump to step 3, skipping step 2. That's what I'm going to do. So I'm going to label all my equations for reference sake. You know, if it's a first equation, second equation, or third equation, you could always look back at the original. So when you're doing your own work, you could cut down on some of these instructional strategies that I'm using. So step 1, going to create a pair of additive inverses with the x term. So I need to multiply this by -3, this one by +2, because they have to be opposite in sign. I don't like to do subtraction. It's harder on the mind to keep track of. And let's see here. So triple and negate. Double. Leave a space. There's no y. If you want, you could write +0y. I've never done that, but I found peers when I was in school used to find that successful. Just more writing. Just leave a space. And double. Okay, add down. See ya. Okay, I just want to double check my arithmetic. Looks good. All right, so that is my A equation, and let's go right to step 3. Let's see here. Because now this is going to be, number 3 is also going to be my B equation. Because it already has the same 2 variables. Now let's see, my plan of attack. Which one has the smallest LCM? So between the y's, it would be -45, or just 45, and between the z's, 13, 26, both relatively prime numbers themselves. So I think that the y is going to give me less of a hassle. So I'm going to eliminate it. So as I do so, as I move these, I want to modify them. So I'm going to take this equation down here, and I'm going to multiply it by 9. And when I take this equation, I'm going to multiply it by 5. Add down, subtracts out to 0, and then I have over here -2z, that's equal to -4. If you get a fraction, double check your work up to that point, but don't think that it's wrong. Fractions are numbers too. Don't discriminate. All right, z is equal to 2. And now I need to finish solving the system, so I have the z, now I still need the y. So 63 doubled is 126, and subtracted to the other side, that's 126 plus 9, but both are negative. And that leaves me with negative 135. Okay, let's see here. 45 doubled is 90, and then tripled is 135, so -3 for the y value. Found z and y, and now go back for step 4. substituting back into the original to find the other one. So x, so I could either go into the first one because that has an x, or in the second one. And the second one is just a simpler equation, so that's the one I'll use. Negative 16 on the left is positive 16 on the right for an x value of 5. Now, I just want to show you, if I would have taken the y value with the z value, that I would still get the same answer. So as long as you have the big ideas correct, you should still get the same answer. So let's see, that would be negative 9, negative 11 on the left, and then that would be 10, and then yeah, x is 5, of course, because it's got to be true for all three equations at the same time. So you don't have to do that. And so finally, the answer is an order triple, alphabetical. And that concludes solving all the varieties of a three-variable system with linears when there's one solution. So now would be a good time to just kind of pause the video, go do something else, have a little brain break, and then I'm going to talk about the special cases when you could have infinitely many solutions or no solution at all. Yeah, I hope you took a break. Welcome back. Here we're going to work with the special cases, starting off with infinitely many solutions. Thankfully, even though there's more conceptual or abstract thinking to go along with these problems, the work is less. That's my kind of deal. And the reason is because you can short circuit the work when you arrive at unique results. So when you have infinitely many solutions, I'm going to remind you that it intersects all the planes in a line, or they're all stacked together as the same plane. And you have to look for two conditions. The first, one pair of equations yields 0 equals 0, which means that they're the same plane, and that's true all the time. And I could pick any x, y, z, and it will work in both equations at the same time, all the time. And you do that after elimination. And then you have to, with another pair, to see if they either form a line, so y equals like x plus 5, or maybe it'll be z plus x equals 2, but a line in 3 dimensions is just any two variables. And or you might get the fact that it also yields 0 equals 0, so then that's the case when all three of them are the same plane. So that was kind of like a two-piece one. You could have either that another pair of equations intersects in a line, that's like one thing, or are the same plane. But you still have to look at all three equations. So to solve this system down here, what I need to do is strategize like I had before. I have all three variables and all three equations, so I might as well just start picking off with the least common multiple. So that would be among the z's. So I have, equations 1, 2, and 3. And for the first equation, I'm going to multiply that by 3. And the second equation, I'm going to multiply that by 2. Triple. Double. Whoops. I'll also have to multiply that second equation by a negative. And lo and behold, when I add them together, I get everything to subtract to 0. All of them were additive inverse pairs. So I'm going to star that information. So that's the first piece. Sometimes the first pair might end up being like the two variable equation. And so then you won't realize that you're about to get infinitely many solutions. In this case, I stumbled upon it on the first go. So now I know I'm in the mode of they're either infinitely many or no solution. So I know these two planes are the same, but maybe the third plane isn't interacting with them at all. Maybe I have these two are the same, like 1 and 2, and then the third plane is parallel. So let's see what happens though. So now I take another pair of the original equations. So let's see. If I stick with the z's again, that allows me to eliminate things really easily. So I'm going to modify before I write down, kind of doing like a math aerial, if you will. I'm going to take this one, and I'm not going to do anything to it. And the second one, I'm going to triple. Add together. All right. So that's a two-variable equation. And so that information paired with the other star together, that means that I have infinitely many solutions. But you have to have both conditions. This is like the first one, and that was like the second one. And so this is like two planes intersecting like so and forming a line. Planes 1 and 2 were the same, and then this one was the third plane. Let's take a look at when you have no solution. So at any time that you arrive at a nonsense conclusion, that means these things are parallel. There is not going to be one common point of intersection among all three planes. Yeah, maybe two of them are the same, but then the third one's parallel, and so forth. Or they might look like when you stack cards together, like I explained at the beginning of this lesson. Moving on. So I'm going to look at my system. The x's aren't so bad, the y's aren't so bad, the z's aren't so bad. So I'm just going to go ahead and eliminate with the x's. So this I'm going to double and negate. This one I'm going to keep the same. Uh-oh. Well, those are all pairs of additive inverses, and that's never true. So I'm done. That's nice. So I realized that that can never be true. So then those two planes in three-dimensional space never overlap. And that's why I get this nonsense solution. It's telling me that there's no common point ever. So that is really cool that the graph and the algebra speak this. They say the same thing, but they just do so in a different language. One's visual and one's what we call algebra. So that's an example of no solution. So overall, we got to see that visually we could have one intersection among all three planes for an ordered triple solution. Infinitely many, it could either be a line or it could be all of them are the same plane, so like three pieces of paper stacked on top of one another. And no solution can look like a variety of situations, but the thing to keep in mind is there's no common order triple. These are the steps, remembering to use two equations to make an A equation, use two other equations to make a B equation, and then you solve that A, B equation, meaning you find both variables, and then with those two, you could then go back to an original equation to find the third for your order triple. Sometimes, however, you get to strategize and make your work faster and skip some steps. As long as you have two of the same variables, then you get to solve that system and then use the results and go back to the original. Or like in this case, after you eliminate a variable in the first whatever original pair of equations, then you can realize that those two variables are already sitting there for you in the third equation. So then you get to have your A and your B right away. So just keep in mind the big picture of what you're doing. Then to review the special cases, definitely infinitely many is harder of the two, and you have to check for all these conditions. You have to get a 0 equals 0 at some point between a pair of equations, and then you also have to make sure that the third plane, when you interact it with one of the other two, forms a line, or if we would have gotten 0 equals 0 here, that would also mean that we have infinitely many solutions, because then all three planes would just have been the same. And lastly, at any time you are working through any of the work at all, and you get a nonsense result, you have no solution. Now that may happen all the way down at the AB phase, where you took maybe the first two equations, and let's say equations 1 and 3, and you found your AB system, and then when you went to solve that, then you got nonsense, and so that would probably be this visual representation.